You, narrator, have you ever stared at your computer screen and wondered, what's really going on here? How does all this information appear on my screen? Well, the answer lies in a hidden language, a secret code that forms the very foundation of our digital world, digital signals. But the digital world is different. Here, information travels in a series of precise bursts, like a series of on-off switches. These bursts are the heart of digital signals, represented by ones and zeros. It might seem simple, but this switch from continuous to discrete makes all the difference. But wait, there's more. This binary code isn't just for on and off switches, it's a powerful language that can represent anything you can imagine, but that's not all. Our devices are like master translators, taking complex information and breaking it down into this special language of ones and zeros. So, how does this transformation happen? How does a smooth analog signal become a series of digital bursts? The answer lies in a fascinating process called analog to digital conversion, ADC. Think of it as a translator taking the flowing language of analog and converting it into the precise clicks and whirs of digital. Here's the trick. The ADC samples the analog signal at specific moments, like taking snapshots. Each snapshot is then assigned a special code based on its strength, kind of like giving each picture a unique ID. Finally, these IDs are translated into a binary format, a language computers can understand perfectly. But there's a catch. To ensure a smooth translation, we need to take these snapshots fast enough. Imagine taking blurry pictures of a fast-moving object. You wouldn't get a clear picture, right? The same applies to digital signals. We need to sample fast enough to capture all the details, following a rule called the Nyquist theorem. But how does an analog signal become a digital one? Through a process known as analog to digital conversion, or ADC. This process is like a translator, converting the continuous language of analog signals into the discrete binary language of digital signals. And it's not as complex as you might think. First, we have sampling. The analog signal is sampled at regular intervals to measure its amplitude. Think of it like taking regular snapshots of a moving picture. Next is quantization. Each sample is assigned a digital value based on its amplitude. It's like giving each snapshot a unique identifier. Then comes encoding. These quantized values are translated into a binary format that the computer can understand and process. It's like converting the unique identifiers into a language the computer speaks. The sampling rate is crucial and must be at least twice the highest frequency in the analog signal, according to the Nyquist theorem. Sometimes we use low-pass filters to remove high-frequency components and prevent aliasing, a kind of distortion. And that's how the magic happens. The analog signals we experience in our everyday world are transformed into the digital language of ones and zeros that our electronic devices can understand. It's a fascinating process, isn't it?